Okay, so we're going to do number 1. Start with part A. So it says a function f has the domain -20, 15, range 1 to 12, and the point -5, 7 lies on its graph. The function h is a transformation of f given by h of x is equal to 3. Function f times 5, parentheses x plus 6, all plus 2. Describe the transformations in any correct order. Okay, so let's break this down. So we have h of x is equal to 3. So we can highlight our different transformations here. So we have this 3 out in front. We have a 5 right here. We have a plus 6 right here. And then we have a plus 2 out here. So if we were just going to label them left to right, it would say this 3 is going to give us a vertical stretch by 3. So let's get our highlighter and do this. And then we'll say this is a vertical stretch by a factor of 3. Okay. And then our blue part here is on the inside. So remember, everything on the inside is kind of opposite of what you may initially think. And so we have a horizontal compression by a factor of 1/5. Of 1/5. Okay? And then our next part is this green part. And we're in the inside, so we're still thinking horizontally, and we're thinking the opposite of what we might think. So it's plus 6, so we're going to shift left 6. And then our last one is this plus 2. And that's going to be on the outside, so we're thinking vertical, up and down. And that's what we think it's going to be. So it's going to be a shift up by 2. Great. So now that we have all of our transformations of what's going on with this graph, then we want to do it in the correct order. So when we think about correct order, I think we're going to do everything left and right first, and then everything up and down second. So the correct order for this, a correct order, I guess, would be our horizontal compression first. So we're going to say this is number 1. And then our shift left as number 2, right? Because those are our horizontal things. And then our vertical stretch will be 3. And then shift up will be our last one. Okay, so part B is asking us the domain and range of our function h. So again, we'll have h of x up here. Right, and I'm going to highlight the transformations that apply to our domain, and then the transformations that apply to our range. So our domain transformations are going to be everything that happens to the x-axis. So we are going to be looking at this 1/5 and this plus 6. So everything on the inside of our f. And then our range is going to be everything that happens to our y-axis, so thinking up and down. So we'll have our 3 and then our 2. Okay, so starting with our domain, we want to look at our domain of the original function f, which is -20, 15. And what we want to do is we want to apply our transformations that apply to our domain. So we want to apply those red transformations to this domain, and only the red one. So we first have that horizontal compression by a factor of 1/5. So what we're going to do is multiply our domain by that 1/5. Right, and so then we're going to have -4, 3. And then we also have this plus 6 on the inside, which remember that's a -6. Then we're going to subtract 6 from both of these. So then our domain is going to be -10, -3. we're going to do the same thing for the range, except, of course, we're only applying the blue transformations this time because those are the only ones that affect our range. So our original domain, or our original range, was -1, 12. And so now we need to apply our transformation. So step 1 is this stretch by a factor of 3. That means we're going to multiply this domain by 3. So then we end up getting -3 and 36. And then we also have to add 2. So then we end up getting -1 and 38 as our new range. So for this one, it's asking us name one point that must lie on the graph of H. Well, we know that the graph of H is a transformation of the graph of F, and we know that the point -5, 7 lies on the graph of F. And so what we need to do is apply our transformation to these points, and then we'll have a point that lies in the graph of H. So step 1 is we're going to use our X first, and we're kind of going to do the same thing that we did with the domain, right? We only can apply the transformations that happen in our domain. So we need to apply the stretch by 1/5 and the -6. So step 1 is to multiply -5 by 1/5. So we end up getting -1. And then we need to subtract 6 from there. So then our new point is going to be -7. So we're going to plot that down here. Great. And so now we need to do the same thing, except we want to do it with our range. So remember, we can only apply what applies to our range and our transformations. So we're going to, step 1 is to multiply by our stretch of 3. So then we get 21, and then we need to add 2. So then we get 23. And so our new point that must lie on this graph is -7, 23. Okay, so we are figuring out which one of these transformations are happening, and then we are trying to make those transformations to this point 12, 6. All right? So if we look at g of x is equal to f of 3 of x. So remember, everything on the inside of our function is going to be horizontal. So we need to think, what could this be? And we look on our list and we see a 3, and we want to think, okay, opposite of what we initially want to think when it's on the inside. So if we see a 3 on the inside, we want to think 1/3. So we come to our list and we see B, horizontal compression by a factor of 1/3. That is what we want. Great. And so now, since on the inside, that's our horizontal axis, that's our x-axis, so we only apply the transformations to our x-coordinate. So we see we have a horizontal compression by 1/3, so 1/3 times 12 is equal to 4, and so our new coordinate point is going to be 4, comma, this should be -6. So then over here we have 4, comma, -6. Now our next function, h of x, we have a 3 on the outside of our function, right? So this is, originally we didn't think this is a 3 on the outside, we're thinking vertical, and it's what we think it is. So it looks like a 3, it is a 3. So we think, let's go vertical, and we're multiplication, so we have that stretch. So then we see C, vertical stretch by a factor of 3. That's going to be us. And remember that when we have something on the outside and we need to change a point, we only deal with our range. So we have 12, 6. We need to do our transformation just to our range, just to our y value. So we have 3 times -6, which is going to give us -18. So that new point is going to be 12, -18. Put that over here. Our next function, I of x, is going to be f times x minus 3. And so we need to think, oh, we're on the inside, we're dealing with something horizontal, left or right. and it's opposite of what we think, and this is a addition or subtraction, so we're shifting. So we are shifting to the right by 3. So we look down and we see E, shift right 3. We drop the E in this box right here. And then remember, if we're on the inside, we're only changing the X value of our coordinate. So we have 12 plus 3. We end up getting 15. So our new coordinate point is going to be 15, comma, negative 6. And we'll drop that over here. Our next function is j of x, and that is equal to f of x with a minus 3 on the outside. And so if we're on the outside, remember we're thinking up and down, we're thinking vertical, and we're adding or subtracting, so we're shifting. And it's on the outside, so it's exactly what we think it is. It's not any different. So we are shifting down by a factor of 3, so that's going to be h over here. And remember, we only do things on the outside because it's in our range. We only do it to our y value. So we have our negative 6. We're going to subtract 3 from that, which is going to equal negative 9. And so our point for this is going to be 12, negative 9. I'll drop that over here. Our next function is k of x, which is equal to f of x plus 3. On the inside. So remember, inside we're thinking horizontal, we're thinking a shift left or right, and we need to think it's the opposite of what we might think. So it's going to be a shift to the left by 3. So now we need to look and we see f. So we're going to drop f right here, and then since it's on the inside, we're only changing our x coordinate. So we're going to have 12 to the left minus 3. It's going to equal 9. So our new coordinate point is 9, comma, negative 6. We're going to drop that right here. Our last one is going to be L of x, which is equal to f of x plus 3 on the outside. So remember, we're thinking horizontal, or we're thinking vertical, we're thinking up and down, and it's a shift. So we're going to be shifting up just like that plus is telling us. So we're shifting up by a factor of 3, so that's g. We're going to drop that here. And remember, if we're doing it up and down, we're on the outside of our function. We're only messing with our y value. So we have negative 6. We're going to add 3 to that. We get negative 3, and then our new coordinate point is going to be 12, negative 3. And we'll drop that right over here. Okay, so we're finding a formula for the function of g as a transformation of the function of f. So let's first look at our x-axis, our horizontal things. So originally we have our function going all the way to 8, but now our transformed function is going from 0 only to 4. So we've cut our horizontal in half, right? We're compressing what we originally had by half. So we can write that down as a horizontal compression of 1/2. Great. And then, now that we know that part, let's look at our verticals. Anything going on vertically? Well, yes. We started at, 1 as our lowest point, right? We can see that. And then 1 is our highest point. And then our transformed graph, we have negative 4 as our lowest point and 4 as our highest point. So we're stretching this vertically by a factor of 4, right? We started at negative 1, now we're at negative 4. We started at 1, now we're at 4. So we're stretching this vertically by 4. Stretch of 4. So now that we have that, we need to put it into a formula. So it's asking us the function of g, so we're going to start with g of x, right? And then what's on the outside? Our vertical stretch of 4, so we're going to multiply by 4. Then we have our f of x, and then we have a compression of 1/2. So remember, it's on the inside, it's flipped of what we think. So a compression of 1/2 is really going to be a multiply by 2x. So this is our function for the graph of g. Okay, so we are writing the function g in the form of our in the square root function, because that's our parent function. So originally we have f of x is equal to the square root of x, and then we have our formula g of x is equal to 3f times negative x minus 2 minus 1. So step 1, I'm going to factor out this negative so we don't get confused when we start using this transformation. And so now we're going to put it into our square root. So we have g of x is equal to, we have that 3 on the outside. We have our square root, and we have negative x plus 2, and we have our minus 1 way out here. Great. And so now it's asking us to write our transformations in any correct order. So remember, let's kind of do what we did on the last one, and let's highlight the things that happen in our domain and the things that happen in our range. So our domain is going to be our horizontal axis, and the things that do that are going to be on the inside. So this negative and this plus 2, that's all going to happen to our domain. And then on our outside is going to be the things that happen to our range, which is going to be this 3 and this negative 1. Okay, so let's look at one of our first domain, our x-axis ones. We have this negative, and we're thinking x-axis, right? And so that negative is a reflection. So we're reflecting over the y-axis, right? Because we're moving left and right, we're thinking x-axis. So we're actually reflecting over the y-axis. Reflecting over y-axis. So remember, everything on the inside is left and right. And so we have our reflection over the y-axis, and then our other domain, our other x-axis transformation is this plus 2. Remember, it's kind of the opposite of what you think. So if it's a plus 2, we're really moving left 2. So it's going to be a shift left by 2. Now let's look at our transformations for our range. We're thinking y-axis. Let's start off with this 3. For multiplying, it's what we think it is. We are stretching by a factor of 3. So this is going to be our vertical stretch by 3. Awesome. And then our last transformation is this negative 1. And that's, again, we're still on our y-axis. We're still thinking up and down. And this is exactly what we think it is. It's going to be a shift down by 1. So when we think about what order these should go in, we want to think about horizontal axis first, multiplication first, then we're going to do vertical axis, multiplication first. So we're going to start with our reflection. We're going to do our shift left, then we have our vertical stretch, and then we finally have our shift down. So it says, write a formula h of x that takes a function f of x and transforms it as follows in order. So a reflection across the x-axis. Okay, remember that's going to be, if we have our graph, right, a reflection across the x-axis means we're flipping it like this, right? So we're really flipping it up and down, if you can think about it like that. And so that means we want to put this negative for the reflection on the outside of our function. So we're going to start with a negative right here. And then it says we have a shift up by 5 units. So then we have, okay, our shift up by 5 units is going to be on the outside again because we're still moving up and down, and we're going to keep it normal. So we're going to say plus 5, okay? So we have a horizontal compression of a factor of 1/3. Okay, so that is going to be on our inside. Remember, horizontal things happen on the inside of our function. And it's a factor of 1/3. So remember, we want to flip it, and we really want to think multiply by 3. So we have h of x. We still have our negative f on the inside. We have 3x plus 5. Okay, our next part is to shift right 4. So shifting right 4 means we're moving our graph to the right, and we're on the inside. We're thinking left and right. We're thinking x-axis. So we're going to put that on the inside and we're going to flip our sign, right? Even though we're shifting right, we're really going to subtract this 4. So we have h of x equals negative f times 3. We need that parentheses, x minus 4. And we still want to keep that plus 5. So this is our final function for h of x. Okay, so we need to figure out if this function is even, odd, or neither. So let's remember how we figure out if a function is even, odd, or neither. So a function is even if f of negative x is equal to f of x. A function is odd if f of negative x is equal to negative f of x. And obviously a function is neither if neither of those are met. So step 1 is let's plug in negative x into our function. So we equal the square root of negative x squared plus 1. And if we simplify this down, we end up getting f of negative x is equal to the square root of x squared, because negative x squared is just still x squared plus 1. So we see that f of negative x is equal to the square root of x squared plus 1, which happens to be our original function f of x. So this function is even. So it's asking us, it says an even function f is decreasing in concave down in the first quadrant. What can we say about the function's behavior in the second quadrant? Well, step 1, let's remember what our quadrants are. So this is 1, this is 2, this is 3, and this is 4. And let's graph this function, well, sort of. It's kind of a rough estimate, and we say that it is decreasing in concave down in the first quadrant. So it looks something like this in the first quadrant. So it's asking us what it is in the second quadrant. Well, we know that this function is even, and what do we know about even? Even functions, they are symmetric around the y-axis. So we want to think about flipping this, almost reflecting what we have to the y-axis. So then we have a function that may look something like this on this side, right? And so we know that the behavior of this function is going to be concave down, and increasing.
Okay, so I'm going to be looking at number 8 here. We have a bathtub that was partially filled with hot water. When the cold tap water was opened, 2 minutes later, the bathtub held a total of 48 gallons. 5 minutes after turning on the cold water, the bathtub held 61.5 gallons of water. So part A, what was the rate of change in the number n of gallons of water from 2 minutes to 5 minutes? Include units. So rate of change, we use our slope formula. So that's m equals, we're going to have basically y2 minus y1 over x2 minus x1. So here we have the points. We know that after 2 minutes, we had 48 gallons. And then after 5 minutes, we had 61.5 gallons. So we just plug these in to our formula for m. So we get that m equals 61.5 minus 48 over 5 minus 2. So m is going to equal 13.5 over 3, or 4.5. So over here, we're going to say m is equal to 4.5. And what are our units? We were concerned with, up here we had gallons, and down here we had minutes. So we get our units are gallons per minute. Okay, and for part B, it's asking how much water was in the tub at the time the cold water was turned on. So here we can kind of go to our y equals mx plus b formula. So one thing we know is that we have the point 2 comma 48 and that m equals 4.5. So if we plug these in here, we get that 48 equals 4.5x, 4.5 times 2 plus b. So 48 equals 9 plus b. So b is going to equal 39. So what that means is that for part B, how much water was in the tub at the time when the water was turned on? We have 39 gallons. And then for part C, write a linear function for the number n of gallons of water at time t after turning on the cold water. So if we go back to kind of like our y equals mx plus b, we have everything that we need to plug this in. So we know n is our number of gallons, so n is equal to our rate, which is 4.5, times our time, t, and then plus our initial amount, 39. So our linear function is that n equals 4.5t plus 39. Okay, so looking at number 9 here, we're saying the cost of X yearbooks is D dollars, where D is a function of X. So the average rate of change is a constant 15 per yearbook. If the cost of N yearbooks is 2,000, what is N plus 1 yearbooks? So because this is a linear rate here, we know that if we increase N by 1, the amount should also increase by $15 per yearbook. So because of that, our cost for N plus 1 yearbooks, cost of N plus 1 should be 2,000 plus the 15 that we get per yearbook that we add on, basically. So N plus 1 is $2,015. Okay, so for number 10 here, we're going to find the equation of a secant line that passes through this function at x equals 2 and x equals 4. So a secant line is a line that passes through at exactly 2 points. So if we look here, what we really want is we want to find those 2 points. So if we plug in 2 and 4, f of 2 is going to equal, we'll have negative 1/2, 2 minus 2 squared plus 1. So f of 2 is just going to equal 1, because this will be 0 plus 1. And then f of 4 is going to equal negative 1/2, 4 minus 2 squared plus 1. So f of 4 is going to be equal, we'll have 2 squared times a negative 1/2, so that's negative 1, and then we add 1, so we'll have 4 minus 2, which is 2. We square that, we get 4, times negative 1/2, we'll have negative 2, and then we add 1, so that'll be negative 1. So we have our 2 points here. So we have the point 2, comma 1, and the point 4, comma negative 1. So now we can find the slope from these 2 points, so we can finish our equation. So the slope is going to be 1 minus a negative 1 over 2 minus 4. Oops. So on top we're going to have positive 2 over negative 2. This is our m. So m is equal to negative 1. So now that we have a point and a slope, we can either use our point-slope equation, or we could use y equals mx plus b and plug in our point and solve. So I'm just going to use our point-slope equation. So our point-slope is that we have y minus some point, we'll use this one right here, times our slope, and then x minus the x value there. So if we distribute this out, we get y equals negative x plus 3. So that's our equation there. 3 minus x. Okay, so I'm going to be working on number 11 here. So the graphs show linear functions in the form y equals mx plus b, labeled a, b, c, and d. Identify which graphs have the indicated properties and explain your reasoning for each. So m is greater than 0, so that means that we're positive slope. So if m is greater than 0, we should expect to have a line kind of like this here. Okay, So that immediately leaves us with just B or C. And then B is less than 0. So if B is less than 0, that tells us where our y-intercept is. So B less than 0, that corresponds to something like that. So the only graph that works for this first one is graph C, because C is the one with a positive slope and a negative y-intercept. So then for part B, we have a negative slope and a positive y-intercept. So if we have a negative slope, we should expect our graph to look something maybe like this. So that leaves us with just A and D. Then between those, which one has a positive y-intercept? So the one with the positive y-intercept is going to be A. So for C, we have negative slope, negative y-intercept. So negative slope leaves us with A and D. Which one of those has the negative y-intercept? That would be D right here. So part C is D. Okay, now working on number 12. Starting with part A, we're just supposed to write a formula for each situation. So part A, we're told median home prices in the US were about $186,000 at the end of 2008 and fell about 2.5% per year for a few years. Let M be the median home price and T be the number of years since 2008. So this is an exponential function. So there's kind of two main types of exponential functions. One of them is where we have our amount equals our sort of like initial quantity, which I'll denote like this, times whatever our rate is to the t. So this is kind of more like our incremental kind of growth or decay, where typically it'll be told that our rate is in like an amount per year or maybe per month or something like that. And then we have our other form, which is this here, so this would be if you have something like a continuous growth or decay, where your rate is sort of continuous and not based on like a per year or per month or something like that. So part A here, we have median home prices in the US were $186,000 and fell per year 2.5%. So that means that we should be looking at this top one up here. So for this one here, our initial amount is at $186,000. And then we have our rate. So if we fall by about 2.5%, the way that we can think about that is that we're doing 1 minus r to the t because we're going downwards. So that gets us 0.975%. So you can either write it as 1 minus 0.025 or just have 0.975 to the t. So as t increases, the median home price should also decrease per year. Okay, so now for part B, Dan had an annual salary of $30,000 when he was hired and has an annual salary increase of 3.2% per year. Let D be Dan's annual salary and T be the number of years. Oh, and sorry, on this last question, I just realized I should say that this is equal to M because it tells us let M be the median home price. So on this one here, we're going to say, so this kind of lines up with this top function up here, where we have our rate based on like per year. So we know that if we increase 3.2% per year, that's going to be 1 plus r to some t. So that way we get like our rate is positive and increasing, right? So if we look, let D is going to equal our annual salary. We have our initial amount, which is this right here, times our rate, which is 1.032 to the t, where t is the number of years. So that's that one. Now looking at part C, we have a population of 1 million, and a petri dish grows at a continuous hourly rate of 8.66%. So notice here it says that this is continuous. So if it tells us it's continuous, that means that we should expect our answer to be like this form here with the e to the kt. So our initial amount that it tells us is 1 million. So we're going to say that our population B is equal to 1 million. E to the 8.66%, we have to make that a decimal. So that's going to be 0.0866, and then we have T. So that's that one done. So then for D, it says initially there is 100 milligrams of radioactive tritium, and it was decaying at a continuous yearly rate of 5.63%. So notice continuous here, which means that we're going to have our amount equals our our initial amount, e to the kt. So this time, if our amount is decreasing, this continuous rate, k, is going to be negative. So if we start this here, we're going to say that our amount is equal to our initial amount, which is 100, e, and then because we're decreasing, we're going to say that this is negative. And then we have our rate, 5.63, as a decimal, so 0.0563, and then our time, t. So that's that one done. And then the last one here, we have part E. The cost of raised auto insurance was $400 in 2020, and it has been increasing by $50 per year since that time. Let T be the insurance cost at time T years. So notice how this one, it doesn't tell us it's like a percent increase, it's a constant amount. So this is actually just a linear function. So we can say that our insurance cost, is just going to be our initial amount, which is $400, plus the amount we increase per year times time. So this is just like our y equals mx plus b form. It's just a nice linear line where we have an initial amount and then our rate that we're increasing. That's all of these ones. And again, just really quickly, if it tells us that it's continuous, we have to use our initial e to the kt. And then if it's not continuous and it's like per year, per month, or something like that, we use this top one here.